Hi Wildcats, this is Unit 2, Focus Question 6, and we are going to look at refraction of light, or what happens when light travels through different mediums that aren't a vacuum. So this focus question and the idea of refraction deals with a lot of the things that we experience like in kind of our everyday lives or that we've observed before. So if you have ever looked at something in the water and then reached out for it, you know that you see it somewhere, but if you reach and touch it, you miss it, right? It's in a different spot. So that's true. Like same thing. If you put a pencil in a glass of water or a straw, it looks different, like it's disconnected. Or even this image that you may be familiar with where light going through a prism, it it then splits and comes out and you get all the different colors. These are all due to this idea of refraction. So let's take a look at what refraction is. Okay, so refraction is this idea that when a electromagnetic wave, again, we're going to use light because it's easy to see, but this is true of all electromagnetic waves. So as electromagnetic waves go through different mediums, they change speeds. And when they change speeds, that causes them to change directions. So here is a light wave. This is a block of glass. So it's traveling through the air. As it goes through the glass, it bends. And then when it comes out of the glass and returns to the air, it bends a second time and now travels straight. Okay, so this is refraction, this idea that it changes directions because it's changing speeds as it's going through these things. So here is that kind of in graphical form. So incident, some vocabulary here. Incident, another way to think of this is the incoming wave. So this is the wave going in to a new material. And this is the refracted ray or the one out or true. Through the material. So this is the incoming wave. Incident means incoming, refracted means out. And so we're going to talk about these. So this is two different materials, air and water. So we would call this angle right here, we would call this theta 1, and we would call this refracted angle theta 2, or sometimes they're referred to as the angle of incidence and the angle of refraction. And it is because of this that when it goes from air to water that we get all these funky things that we see, right? Like um, this duck is definitely alive and not split in half, but when you look at it, the rays are coming at your eyes differently. The light rays, light waves, are coming at your eyes differently because this is air to air and this is water to air, and they bend. That's what's happening. Why this person's eye looks so weird through this glass is because the light rays have to go through the air, through the water, and then to us. And as a result of that, they bend in that process. Okay, so why do they bend? So they bend because their speed changes. And there's a number of different examples, I think, that I think help with this. If you were in a marching band, some of you probably are. If you are in a marching band and you are walking on concrete, you are going to go one speed. However, when you get to this line, if on the other side of this line is swampy, dirty, mushy ground, as you go through, you will slow down. It will be harder to walk. And as a result of that, this whole line will start to bend. The people behind you are continuing to go the same speed, so they are also going to catch up with you, causing this bunching up effect. So if you'll notice, there is some distance between these two dots, or two people in the marching band. Over here, when they are going slower, that distance has gotten smaller. And that is because these people behind are starting to catch up to these people that are moving slower. In terms of this bending, I think a good way to kind of visualize this is maybe you've seen those toys that have two wheels and they roll. So let's say this is a hardwood floor and carpet, right? So as these two wheels are going on this line, what's going to happen? This wheel is going to hit the carpet first. Okay, so when this wheel hits the carpet, it is going to slow down. It's easier for it to move on the smooth floor than it is the carpet. So because this wheel slows down, but this wheel is still moving fast, the whole object is going to start to bend, right? This wheel continues to go fast and it causes it to bend. So that is the bending due to change in speed. When it hits on an angle, it doesn't hit, it's not directly. So now, if this toy were going, use a different color, if this toy were going perfectly perpendicular to the surface, both wheels would hit at the same time and the light would not bend. So this only applies when we are talking about light or electromagnetic waves coming in at an angle. And because they come in an angle, part of the light ray hits first and that causes the whole light to bend. Okay, and so that's what you're seeing over here. You're seeing that the light comes in, this side of the wave hits first and slows down, so then it starts to turn in this direction. Additionally, because now these are in the slower medium, they are moving slower where the lines behind are moving fast, you get the bunching up of all these wavelengths, and so that actually changes the wavelength as well. Okay, um, this is called, all materials have an index of refraction. Index of refraction is the factor, so it's a factor by which the speed of light is reduced. So when there is no medium to travel through slash a vacuum, light is going as fast as it possibly can, 3.0 times 10 to the 8th meters per second. In any other medium, there's more particles and therefore it slows it down. So air, and this chart is a measure of that index of refraction. So air, you can see, is, I guess I could put vacuum down here. So a vacuum would be a perfect index of refraction of 1.0, right? So this means it's traveling 3.0 times 10 to the 8th meters per second. And then from here, these values change that number. They decrease it. And so the denser the material, the higher the index of refraction. So you can see really dense things like solids and glass have much higher index of refractions than liquids, and those are higher than gases like air and carbon dioxide. Okay, so the symbol for the index of refraction is just a lowercase n, and the unit is none. Okay, so this is a factor. It's not like a quantity, it's just a factor that we use to adjust the number, the speed based on this factor. Okay, so it is a unit list number. There is no unit, and we'll see why it actually works out that way in a second here. Okay, so let's take a look at the math behind the index of refraction. We can calculate this, or we can figure out how the speed changes, since this is a factor. So if we want to know the speed of light in a given medium, like let's say water, we would simply take the speed of the light in the vacuum. So this is going to be 3.0 times 10 to the 8th meters per second, and we divide it by that index of refraction, or n. So we could actually do this. Water is 1.33, so we would take 3.0 times 10 to the 8th meters per second. Now, if we divide this by 1, we get the same number, right? And that is why the index of refraction for a vacuum would be 1, because it's always 3.0. The higher this number, the higher the index of refraction, the smaller this speed is going to be, the more it slows down. So if we take water, 3.0 divided by, or times 10 to the 8th meters per second divided by 1.33, you can throw this into your calculator, but you would see this would be a lower number than the speed of light in a vacuum, and therefore electromagnetic waves, light travels slower in water than it does a vacuum. Okay, we also talked about how because these waves behind in, say, the vacuum or whatever the medium is, are still moving fast while these are moving slower, the wavelengths get closer together than they are over here. And so that means we need to be able to calculate the new wavelength that actually changes the wavelength of the electromagnetic wave, light in this case. And that can be done by taking the wavelength of light in a vacuum. So this would, you have to be a known value. You could look at your electromagnetic spectrum chart and say, red light has a wavelength of this. If I took the index of refraction, I could use algebra and rearrange to get the wavelength of light in the new medium. It also allows us to figure out if we know the wavelength of light in the vacuum and the new wavelength in this new medium, we could use that to solve for the index of refraction. So the important thing to understand here is that the index of refraction does a couple things. One, it describes how much the factor by which the speed of light will slow down, and we can use it to determine the new wavelength of that light or electromagnetic wave in this new medium. Okay, this is kind of all put together into what is called Snell's Law. Snell's Law describes what's happening here. So we can see the change in the speed of the direction of the refracted wave. It's dependent on the angle that it goes in at as well. So we said before, if it's going in completely perpendicular, then the wheels, right, in our example, hit at the same time, and so it carries on in a straight path. But if it goes at an angle, we get bending, and that how steep that angle is affects how much the light bends in this new medium, as well as the index of refraction. And so we can summarize this. We would say the index of refraction, or the index of refraction of the original material, so N1, this would be N1, times the angle of incidence, right here, the incoming angle, is equal to the index of refraction of material 2 times this refracted angle, or the refracted angle, or theta 2. So this equation allows us to predict the angle at which light will bend as it goes into that new medium. Why would we want to do that? If you wear glasses or contacts or know someone that does, this is in large how they figure that out, right? Contacts, glasses, are quote unquote glass, they're not anymore. But contacts, glasses work because we need to bend the light to make it hit a different spot in the back of your eye, so that the image is focused. And we need to be able to know how much the light is going to bend as it goes into that material. So there are many examples of why it's useful for us to be able to predict the angle that it goes in at, but maybe one that we're most familiar with are glasses and contacts. Okay, that is kind of a big overview of the index of refraction. We're going to do some labs to kind of test this idea, to test Snell's law, and then use it as well to make some predictions in class. So we will work with this idea, but hopefully this is kind of a good introduction into what is refraction and how it affects speed, wavelength, and how we can predict the outgoing or even incident angle. If we know the angle it's coming out at, we could tell what it's going in at, as well as the index of refraction, and that is Snell's law. So I hope this helps as you kind of organize your thinking around refraction for Unit 2 Focus Question 6.